Three, two, one. Okay, here we are, another 2070 online video. And I'm pretty excited. I'm pretty excited because we're going to be talking about my all-time favorite mathematical structure, vector spaces. So let's motivate this beautiful abstract nonsense with some motivation. So far in your math journey, you've encountered several types of scaling and adding. In this class alone, we've seen it happen twice. So, for example, if I take some vectors, I can scale them and add them, and scaling and adding goes how you think it should go. Right? When you scale, you multiply every entry by the scalar, and when you add, you match entries and add them up. Right? Component-wise operations. It happened again. For matrices, same deal. If you want to scale a matrix, you scale the entries, and if you want to add two matrices, you add the entries. No more, no less. Right? And before you got here, you most likely encountered some calculus, and there we talked about scaling and adding. We scaled and added functions all the time, and again, the scaling and adding went how you pretty much thought it should go. If you scale a function, you just scale the outputs uniformly, and if you add two functions, you just add the outputs. Right? So that's all it was. But note here, these are very different objects, right? A vector and a matrix and a function are very different, and how we interact and work with them, right? Certain things we do for vectors that don't necessarily carry over to matrices. Certain things we do for matrices don't necessarily carry over to functions. Certain things for functions don't necessarily carry over to matrices, right? So in calculus, right, we take derivatives and limits of functions. And maybe you can do that for matrices. I don't know. But I do know you can. But we're not going to get into it. But the point is, right, as math objects, these are very different. But we can kind of see there's this huge similarity here going on. There's like a pretty meaningful way of scaling and adding in a very deliberate way. And so, whenever we see this kind of pattern where we have, in multiple settings, similarities, in mathematics, we like to generalize and study the things more abstractly. So, I have scaling and adding for these three very different collections, and it would be great if I just knew how scaling and adding worked on their own without getting hung up on, do I have a vector, do I have a matrix, do I have a function? And that leads us to define the notion of what a vector space is, and this is a collection of objects. We call them vectors, but they aren't necessarily vectors, where scaling and adding makes sense. And to make that a little bit more precise, that means for a real number alpha and vectors x and y and v, then I have the access to the following elements in our vector space v, alpha x, and x plus y. So I have a collection where scaling and adding are defined. Now, in addition to that, I need to also tell you some things about how scaling and adding work. I just can't declare that I have scaling and adding. Well, what does scaling really mean, and what does adding really mean? Right? In those settings of vectors, matrices, and functions, we had access to scaling and adding, but they had certain algebraic properties and certain equational manipulations that we did with them. So what we want is our vector space to not worry about what type of object I have, but just worry that scaling and adding on their own are behaving. So I need to start off with a list of rules, and then from there I can derive all of the other things. So we need to cook up a list of axioms that scaling and adding should have. And here they are. So let's start off with a pretty basic one. Adding is associative, meaning that, note, the way addition is defined, you give me two objects and then I can add them. Right, but I didn't tell you what happens when you try to add 3, or 4, or 5, or more. That's what associativity tells us. It says that, yeah, you can do that, right, because it's binary, right? You have to give me two objects to then add. Well, then I can add a third object, but as we can see here, you can place your parentheses and potentially have two different things, so we would like things to be nice and associative. And for the most part in your math life, everything you're going to encounter is associative. There are non-associative things, such as the cross product in Calc 3, and other more exciting non-associative stuff for the Lie theory enthusiasts. And Lie, not my last name. Very unfortunately, I can never get a math object named after me now. Lie algebras, and he's already ruined it for me. I can never get that. Anyway, so another thing about addition that we know to be true is that it's commutative. So if I do x plus y, I should get y plus x. That's good to know. Another thing is that there should be sort of a neutral element, a identity, or as we'll call it, the zero element. So traditionally, when people are talking about vector spaces, they kind of just write zero, and they're like, yeah, you know what I'm talking about. But I like to do a subscript v to indicate that it's the zero element associated with the vector space v. And it's precisely what you think it should be. Adding it doesn't do anything. But you can concoct weirdo vector spaces where this is like not actually anything involving the number zero. So I like to put the little subscript v there to indicate what's really going on. Alright, so addition also comes along with negatives. So for every element in a vector space, there is a negative x that does what you think it should do. Adding it gets us to the zero element. There you go. Right, and here is where I like to joke that there really is no such thing as subtraction. There's adding negative elements. Okay, with those four rules, that's pretty much how addition should behave in a vector space. Right, that's how when you say addition to somebody, you expect whatever you're adding to basically satisfy these four things. And for the deep lore enthusiasts, these four rules here create a math object called an abelian group. Ooh. If you drop the commutativity, that's just a plain old group. If you drop the inverses, you get what's called a monoid. If you drop the zero element, then you get something called a semi-group. And if you drop all of these axioms and you just have an addition, you call that a magma. And then there's other things like quasi-groups and loops, and it gets good. It gets good and silly. Go check out the Wikipedia pages for all this stuff. It's a great time. Alright, well, so that's how addition should work, but so far, note, I haven't mentioned anything about scaling, and I want to stress something. Note, I haven't mentioned anything about scaling yet. Look what I'm highlighting. We'll revisit that in a moment. Alright, but how should scaling work? Well, scaling should interact with our operations accordingly. So, in fact, if you scale a sum, the scalar should distribute. We're all good on that. Distributivity is very important. Next up, if you scale by a sum, you get the sum of the appropriately scaled elements. And this result is, while visually very similar to the previous one, is communicating something much more sophisticated. Note this plus sign is the vector addition, and that's the vector addition. This is the addition of the real numbers. This is the addition of the vectors. So there's kind of a conversion going on here. So I love this axiom. This one's my favorite. And as we'll see in a moment, there's a lot you can do with this one. But this one, because there's kind of this neat little subtlety going on here, I've always really enjoyed this one. All right, and similar to that, if you scale by a product, you get the scaled elements accordingly. And I've got a parenthesis goofery that I need to clean up right there. And and there it is. Right, the parenthesis was in the wrong spot. Anyway, if you scale a product, it's the same thing as scaling a scaled element. And again, there is sort of this conversion. This is the multiplication of real numbers. This is the scaling of a vector. And finally, it'd be a weird situation if scaling by 1 didn't do what we wanted it to do. All right. Cool. Now, if you really pay attention here, you might notice something. If you're feeling really abstract, you might go, hey, scalars just seem to need adding, multiplying, and an identity. You're right, and you can go totally bonkers and study not just vector spaces, but things called modules. Oh, boy. And that's when you know you've gone off the deep end. When you're messing around with Banach bimodules, then you're just you're lost at that point. Anyway, all right. So for us, these are the rules, and again, all of these rules are just here to tell us that algebraic manipulations involving scaling and adding behave exactly how they did before. We've extractified the notion of scaling and adding to just a general collection of objects, whereas before we would have a vector, or we'd have a matrix, or we'd have a function, and we know that we can manipulate scaling and adding in certain ways, and these axioms, these rules just say all of those things you've done before are still true. Now you need to derive them, you need to prove that they're true, and for example, you would believe that scaling by 0 should get you the 0 element, and indeed it does. So you start with 0x, this is equal to 0 plus 0 times x, and as we noted, hey, that distributes, and at this point then you add the negative of 0 times x to both sides. That knocks out one of them over here and turns this into the 0 element, and there you go. Multiplying by 0, scaling by 0 does what you think it should do. Nice. And if you think this is beautiful, and that was super cool and super neat, and you're really into that, then I recommend you take Math 201 and then take some more theoretical math classes, because you do it and get a minor, and then also turn that into a major. It's only like a few more classes, so come on. Come on over, join us on the dark side. If you saw this and thought this was like the worst thing you've ever seen in your life, understandable, have a nice day. Okay, and I'm not going to do it, but on your own, as I mentioned, this negative x is defined independently of -1, but you can verify that, yeah, scaling by -1 does what you think it should do, and the argument is a little similar to the one I just did right here. In fact, it uses what I just proved here. Ooh. Alright, cool. Alright, so that was our first taste of the exciting world of vector spaces and beautiful abstract stuff. Let us now introduce a concept that we've sort of touched on but haven't really dug into exactly. A subspace of a vector space is a subset with the following properties. It has the 0 element, it's closed under adding, meaning if you add 2 elements in your subspace, you do not escape. And it's closed under scaling. If you scale an element, it does not escape. And a better way of thinking of this, if you don't like that little list of things, is that subspaces are precisely... What the hell is this word? What? I don't know how to spell. My 11th grade English teacher, Mr. Caravana, he is out there somewhere right now, and he's shaking his head. All those spelling quizzes that I failed. That'd be wild if he's like watching this. Somebody watching this, find Mr. Caravana from West Islip High School and tell him that I still don't know how to spell. Alright. Anyway, so a way of thinking about subspaces is that these are precisely the vector spaces within vector spaces. And these are pretty naturally occurring, and let's start with some kind of simple examples. We'll get more sophisticated in the next video and talk about some fundamental subspaces. But a good one to keep in mind, and I like to just keep this one in mind, in R2, if you look at the collection of elements that have a real number up in the top and a 0 on the bottom, this counts as a subspace, right? Obviously, the 0 vector is in here. Adding 2 elements that look like this will still look like this, and scaling an element that looks like this will look like this. So it's a subspace, and note that it's basically just the real numbers, which we also know have to be a vector space, because I have scaling and adding defined there. Scaling is just multiplying. And no, it's a copy of the real line living in R2, so I've always thought this was a good example to always keep in mind. And you can abstractify that further. You can do like planes in R3 or subspaces, and again, we'll get into a little bit more in the next video. But it's worth noting that it's pretty easy to cook up things that can't be subspaces and thus can't be vector spaces. So for example, if I changed the requirement here from t as a real number to t as any non-negative real number, then this fails to be a subspace because the element 1, 0 doesn't have a negative, right? If there was an element that added to this that got me the 0 vector, well, it'd have to be -1, 0, but that doesn't belong to the collection. Some more interesting subspaces, one that we're going to play around with a lot throughout the semester, is the set of polynomials of degree at most n. So these are the functions that look like that. And again, clearly the zero function is of this form, just make sure all the scalars are zero. Scaling anything that looks like this will still look like this, and adding two things that look like this will still look like this. So this is a subspace in the collection of all functions from the reals to the reals, and thus our vector space in their own right. My personal favorite subspace, the subspace that I live here. I just hang out here. This is my home. This is my safe space. The collection of all continuous functions on the set 0, 1. I cannot tell you how much time I've spent here. It's great. You'll love it. It's a way of life. So as we learn in our calculus days, you can scale continuous functions and remain continuous, and you can add continuous functions and remain continuous, and you can replace the C word here with the D word. The set of differentiable functions is also closed under scaling and adding. And we'll visit those here and there throughout the semester for some spicy examples. Now, before we go on, it's worth mentioning that in any abstract vector space, there were always two subspaces that are present, the set consisting of just the zero element and the whole space itself. Obviously, you need to have at least this element in your set, and for the extreme thinker, you might recognize, hey, wait, I can just only have this, and this has this element, it's closed under adding. If you add this to itself, you get itself, and if you scale this by anything, you get back to itself. So not shocking that this is a subspace, and it's a useful one to have because it's going to turn out that we're going to be very interested in when certain subspaces are what we call trivial, meaning that they are the subspace only consisting of the zero element. The whole space being a vector space is kind of a weird thing to think about, because when you think about a set, it takes a moment to really think that, yeah, it is a subset of itself, technically. And while that's true, there's that part of your brain that might go like, well, and why, and so, yes, and. But it turns out that having access to this is very useful, and for a very specific reason, which we'll now discuss. Let's wrap things up today by revisiting some language we've used, but let's put it in the context of vector spaces. So a span of a list of vectors is the collection of all linear combos. So the span of v1 to vn is just all the things that look like those scaled and added up. Right, we've already encountered spans and worked with them, and we know that they are very important in terms of how matrices behave. And note that span is a subspace, and it's not too hard to see that if you take a linear combo of elements, scaling them still gives you a linear combo. Likewise, adding them still gives you a linear combo as well. And obviously, if I scale everything by zero, I've got the zero element. So, hey. In fact, it doesn't take too much effort to actually verify that the span must be the smallest subspace containing these elements. So if you wanted to really go abstract and talk about what's the span of any subset, not necessarily a finite list, well, because you know that V is a subspace, that means there are always subspaces containing your elements, and then so you just look for the smallest one. There is one, so you just got to find the smallest. Now, for the more mathematically inclined, you might recognize, well, wait a minute, you need to prove there's a smallest. You can. All right. And on the flip side, given a subspace, we say that a list of elements spans it if it's equal to the span. Right, so we've kind of already talked about this. We talked about the standard basis elements spanning Rn, but now we can talk about more exciting things like the list of polynomials 1t and t squared spanning the collection of all polynomials of degree less than or equal to 2. Pretty cool. Hey, note, P2, but I had 3 things. That's interesting. All right, and let's wrap up this video today with a fun question. So like I said, C01 is my buddy, my best friend, my best math friend, I guess. My real best friend is a guy named Joe. But C01, my best math buddy, can you find a collection of functions that span it? Ooh. Now, for polynomials, right, it's pretty easy to find the polynomials that will work, like 1t squared, even if you go all the way up to any possible power that spans all the polynomials. But note that there are continuous functions that aren't polynomials. E to the x is not a polynomial. It is a power series, though. Ooh. So I'll leave this question for you to explore on your own. The answer, not the super spoiler. The answer is, well, I don't know if you can find it, but it's out there. So I'll leave it at that. So next video, we'll look at some more concrete examples of subspaces, some fundamental examples.